So this is just the abstract that you've already seen, so I'll skip right over that. As probably everybody knows, the ultra deep field image, while very beautiful, is also misleading because all the stuff that glows, the stars, the nebulae, and so forth, represents about half of 1% of the cosmic density. The other 99.5% is dark. What is it? This is an image that my wife and I used in our recent book, a popular thing. So dark energy, 70%, cold dark matter, 25%, and atoms, about 5% atomic matter, or baryonic matter, but only a tenth of that is visible. Focusing in on the visible, of course, that's based on the Great Seal of the United States, the back of the dollar bill. Nova Ordo Seclorum is the new order of the world. And what we know is that the universe starts out with stars. Uh-oh, it's not advancing. That's annoying. Ah, okay, good. So the stars start out just made of hydrogen and helium. And all the other atoms are made in stellar processes. And so the periodic
Thanks
table.
for that nod. Yeah.
Heck. This seemed to work fine when we tried it before. So the other stars, the other material is all made in stars. And let me go back to the play mode and hope that this works. So this is the latest version of this plot showing the merging black holes, the black hole neutron star and neutron star mergers. Another neutron star merger besides the one that we saw in 2017 was discovered. And then another possible neutron star black hole merger. So this periodic table shows, this is Jennifer Johnson's work at Ohio State, and it shows by color the origins of the elements. And notice that many of them, especially these heavy ones, come from merging neutron stars or other R process locations. But now we know that merging neutron stars are very efficient at producing them. So here's another one of these diagrams that shows the different, the dark energy, dark matter, and the small amount that's actually visible. So the basic picture is dark matter ships in a dark energy ocean. Imagine the entire universe is an ocean of dark energy. On that ocean sail billions of ghostly ships made of dark matter. But we don't see the ocean, we don't see the ships. All we see are the beacons of the mass of the biggest ships. Those are the galaxies. So in our popular writing on this, my wife and I call this the double dark theory. Dark matter and dark energy are really controlling. So the cold dark matter theory, as Chris said, I had something to do with originating it. So this is a diagram that George Blumenthal and I first showed in talks in 1983. And I featured it in my Verena lectures in 1984. The piling up of fluctuations on scales smaller than about 10 to the 15 solar masses occurs because those scales enter the horizon. They come above this dashed line, plotting amplitude versus scale factor. They come above the dashed line, they come inside the horizon. at more or less the same amplitude. Here we're assuming it's exactly the same amplitude, so purely scale invariant. But then they don't grow very much because the universe is dominated by radiation in these early eras. The transition from radiation to matter dominance occurs at about a redshift of 3,500. And when matter dominates, then they all grow in parallel, the amplitude growing proportional to the scale factor. So you get this piling up, and that fluctuations on scales smaller than 10 to the 15th. And that's why you have this flattened cold dark matter spectrum on those scales. So this is the power spectrum. And if we zoom in on this picture, then we can see that what the picture is basically predicting is that you get dwarf galaxies starting to form at redshifts of 20 or 30 or something like that. Milky Way mass galaxies starting to form at redshifts above 10, clusters starting to form quite recently. And the basic pattern remains the same, even though this was a pure omega matter equals 1 universe that we talked about back in those days, although we also considered in our first paper on this the omega matter equals 0.2 as kind of a lower limit. But this is basically the right picture. And in many other ways, the theory has turned out to be a very good predictor of what we actually saw. So this is the cold dark matter spectrum, the mass variance versus mass scale. And as you can see, this is an old picture, but the data just keeps getting better and the agreement keeps getting better. So from scales across more than 10 orders of magnitude in mass, the amplitude of the mass variance is very wide, very correctly predicted. In addition, the data from Planck and now from ground-based telescopes wonderfully confirms the predictions of the cold dark matter, the lambda CDM theory. There's 6 variable parameters. We had a pretty good idea what they were, and you adjust them to fit the data, and then you get essentially a perfect fit. Well, at least we thought it was perfect. There is this problem, though. If you look at the prediction from fitting the early universe, getting those wonderful agreements, and then using lambda CDM to extrapolate to find what the Hubble parameter is, the expansion rate of the universe is today, you get 67.4 plus or minus about a half. And other combinations of early universe data very consistent with that. But most of the measurements of the actual redshift, the actual expansion of the universe are giving us values more like 73. The one exception is this 70 value, plus or minus about 2, from the tip of the red giant branch. So that's sort of intermediate. But if you take seriously the error bars on these measurements, you have somewhere between a 5 or 6 sigma discrepancy between the local measurements of the actual expansion rate and the expansion rate that you get from early universe data extrapolated to the present with lambda CDM, suggesting either that there's something horribly wrong with the measurements or there's something seriously wrong with lambda CDM. And there are many proposed solutions to this, but the one that I found most plausible physically and also easiest to implement is called early dark energy. So how does that work? Look here on the right. What you see is in dashed the standard lambda CDM picture, where the contribution of dark energy is negligible until you get to redshifts less than 10. And then very rapidly, the dark energy contribution, the blue dash curve, zooms up because the matter is being more and more diluted by the expansion of the universe. Now, the early dark energy scheme arranges to have a scalar field, which is trapped by Hubble friction, we call it. So it doesn't move, and it's set up to be a little bit above the minimum of the potential. And that corresponds to a dark energy because, of course, there's a contribution to the energy momentum tensor proportional to the Lagrangian, which has a minus V, minus potential energy. So if the potential energy isn't zero, that multiplies G mu nu, and it behaves like a cosmological constant, except that it's changeable. So it becomes important, and you can arrange it to be important, right around this time of transition between radiation dominance and matter dominance. And then you want it to very quickly disappear by having the scalar field rapidly go down to the minimum of its potential. And it's fairly easy to make that happen in models. Now, what my group did, I got my old collaborator Anatoly Klipin to run some big n-body simulations. And what we found is that we get some significant changes from standard LEM to CDM. Before I do that, let me just mention this interesting paper by Mike Boylan Colchin and Dan Weiss that showed that one consequence of this increase in the Hubble parameter from the value from the Planck scale, the Planck value is like 67.5, is that the reionization era corresponds to an earlier period in the universe. Corresponds to it's early, but the universe is only 13 billion years old, not 13.8 billion years old. So it has to occur closer to that 13. And also the oldest globular clusters like M92, which has an age we think of about 12.75 gigayears, instead of being at a redshift of about 5.5 in the standard lambda CDM, it would be at a redshift of about 10 with a fairly big uncertainty. Question is that plausible? I don't know any reason to think that it isn't, but it's something that's worth investigating. Now, these are our results. This is from this paper that we just recently published, where we ran these big n-body simulations to see what the effect of the early dark energy is. And on the top, we're showing the early dark energy over lambda CDM -1. So this is the increase over lambda CDM. And at redshift 0, there's a very small effect. It's mostly less than 10%. And on the galaxy scale, it's much less than that. But at redshift 1, for clusters of mass about several times 10 to the 14 solar masses, we're getting an increase of a factor of 50%. And if you go out to redshift 4, for massive galaxies and small groups that are forming then, you get an increase of a factor of 2. And at reionization time, redshifts of 6 or 7, factor of several. So these should in principle be detectable. For example, there's this big census of all the clusters out to redshift 1 by E Rosita. The problem, of course, is going to be measuring the masses of their dark matter halos. But this is showing that there are important predictions. There are many different models. The one we used was the top of this, Tristan Smith et al. For these simulations. That team now favors this Berge et al., very similar parameters. That's a better fit to S8, the large-scale structure data from weak lensing. We predicted this small increase in the baryon acoustic oscillation scale. We would like to do high-resolution simulations so that we can actually track merger trees and substructures and so forth. And we may be able to do some very big paired simulations of lambda CDM plus early dark energy. Now, there was a talk yesterday, an Aspen colloquium, the Aspen Center for Physics, by your colleague, Colin Hill. And I was absolutely astonished with what he told us. This is what one of the slides he showed. ACT, the Cosmology telescope, is driving a preference for non-zero dark energy at the 99.7% confidence level. That is astonishing. Another one of his slides shows that this is occurring not just at one scale, angular scale. This is L of 500, 1,000, 1,500, and so forth. But it's occurring all the way across the scales down to very small angles, very large L. The data they already have in hand that they're analyzing and will be published in a few months as data release 6 from ACT. If that is an agreement with the data they've published so far in this paper that just appeared this morning on the archive, that'll be a 20 sigma or greater detection of early dark energy or something like it. This is the abstract of the paper. I know you're not gonna have time to read it, but let me just emphasize, we find that a combination of ACT, et cetera, plus BAO, prefers the existence of early dark energy at greater than 99.7% confidence level. And a powerful test of this scenario is anticipated with near future data from ACT and other ground-based experiments. Well, that's the end of the first part of the talk. Anyone like to ask some questions? I'm not hearing anything. Is everything okay?
Everything's fine. All is clear. We don't have any hands raised at the moment. People are perhaps in
Yes.
shock still at the moment.
Okay, well, back to...
Yeah, I think you can go ahead and proceed.
Wait a second. What happened to my my slides? Let me open up the Keynote again. Now, there we go. Okay, on to galaxy formation. So as you know, almost all the stars today are in large galaxies like the Milky Way or...
Sorry, Joel, I'm not seeing your slides. Are you sharing?
Thank you for telling me.
There we go.
Good. So today, the stars are mostly in big galaxies like the Milky Way or the big ellipticals. But in the early universe, most of the galaxies were pickle-shaped. They're prolate, like this little image that I'm showing you. We're still, I think, not very sure exactly how galaxies form. And this is, of course, a major area of research. The infrared capabilities of Hubble were tremendously increased by the installation of Wide Field Camera 3 by the astronauts' last visit in 2009. And the reason this was so important is that it allowed us for the first time to see the visible light, the optical light, and not just the rest frame ultraviolet at redshifts of around 2. So in this image at the top, on the bottom, you see the best long wavelength that we could get from the advanced camera for surveys.
Joel?
Yes.
Sorry.
Yes, hi.
We were muted in the live room, and there's actually a question from Chris McKee over here for the previous section.
Okay. Shoot.
Yeah, hi, Joel. I just wanted to ask, at the beginning of your talk, you mentioned that there was perfect agreement between the observations and lambda CDM, and that was my impression. So now you're showing that these significant deviations that seem to be fit by EDE. How did that happen?
It's because the Planck data hasn't changed. And if you just look at the Planck data, you get this tremendously good agreement. What I showed you was ACT data, the Atacama Cosmology Telescope, and this brand new paper now using much more new data. And the data is certainly competitive with Planck, and the data they have in hand in terms of its constraining capability will be greater than Planck, the data that they're in the process of analyzing. So what their preprint says is that right now, that data very strongly favors the early dark energy theory over lambda CDM. And it's about at the 4 sigma level, I think.
And is that the same range of length scales?
No, it goes out to, well, I don't want to go back and show the slide again, but
That's fine.
because you can see it if you look in the preprint, which is now on the archive. It just appeared today. Colin Hill et al. But what they say is that it's across all length scales, all angular scales. And of course, the ground-based telescopes go out to about twice the L value. So instead of L of about 1500, they're going out to well beyond L of 3000. But what they showed was that at all scales, they are somewhat discrepant from Planck and much more in line with what we would expect from early dark energy. Again, this is not my work. This is the ACT gang. So, it's your colleague, Colin Hill, who is the first author of the paper. So he's the person to ask about this. He's in Aspen now, but I guess he'll be back sometime soon. Okay, let me go on with the galaxy stuff. So for people who are familiar with galaxies, you'll know that these are 2 of the major discoveries in the previous decade, that there's this so-called stellar mass halo mass relation. So this is the ratio of stellar mass over halo mass, and it peaks out at about 3%. And that's significant because, of course, the baryonic contribution to the total mass density of the universe is about 16%. So what this is saying is that only about 1/5 of the baryons are turning into stars, even in the galaxies like the Milky Way, around 10 to the 12 solar masses, that are most efficient. And both lower mass and higher mass galaxies are not turning these baryons into stars very efficiently. The other key discovery that we're going to be alluding to is the main sequence, and that is that the star formation rate is more or less proportional to the stellar mass. These are different redshift intervals, and what you see is that except at the largest stellar masses, I'll just ignore that phone. Except at these very large scales where there's a bit of a turn down, you're getting star formation rate proportional to mass, or star formation rate over mass, stellar mass, more or less constant. So this is called the main sequence in analogy with the stellar main sequence. So our galaxy's disks, I think I was fairly typical among astronomers in thinking that galaxies probably start out disk-like. And the reason was basically the same as the reason that we think that, and now know, that planetary systems start out as disks. So Newton didn't know these things. Newton's laws explain why planetary orbits are elliptical, but not why the planetary orbits are nearly circular in the same plane and in the same direction as the sun rotates. Laplace explained this as a consequence of angular momentum conservation, as the sun and planets forming in a cooling and contracting protoplanetary gas cloud form a disk like this one. And this is just a sample of 20 of the many such disks that the ALMA telescope array sees that really are just as the Laplace picture would have led us to expect. So what about galaxies? Do galaxies do the same thing? As the gas contracts within the dark matter halo, it will speed up, and the disk configuration is certainly what you'd expect. But that's not what we see. Galaxies mostly start out prolate, that is pickle shaped. And I'm going to show you that's a consequence of most galaxies forming in prolate dark matter halos oriented along massive dark matter filaments. So this basic picture that you would get this filamentary structure was discovered decades ago by Zeldovich and his group. And this is a page from selected papers by Zeldovich, published after his death. Died in 1988, and this was published in 1992. So it's pancakes forming first, or blini as the Russians would have called them. And then where the pancakes overlap, you get these filaments. And where the filaments meet, you get nodes, which are where structures actually form, galaxies and clusters and so on. One of my graduate students, Brandon Allgood, led what I think is still regarded as one of the most important papers on the shapes of dark matter halos back in 2006. So this is a figure from that paper, and it shows you that this is plotting the short over long axis, C over A, of the dark matter halo shape, treated as an ellipsoid. What you see is that a halo that starts out at, say, 10 to the 12 solar masses at redshift 3 grows in mass, but it becomes more spherical as it grows. In other words, C over A gets closer to 1, but it's never very close to 1. And so a Milky Way mass galaxy today has a ratio C over A of about 0.6. Although when it formed, of course, it was a much lower ratio. And that means that the inner part of the dark matter halo is very prolate. And if you actually look at how these form, they form on these long dark matter filaments. As the filament gets thicker, the accretion becomes more spherical. But the inner parts are still quite prolate. And this is an update of the Arjun van der Velde et al. Study in 2014 that first showed that the vast majority of the low mass, high redshift galaxies are prolate. So prolate, 2 short axes, 1 long axis, that's the blue region of the diagram. And what you see is that for the low mass galaxies, a majority of them are prolate down to redshift 1, and 40% are still prolate down to redshift of 0.5. A little higher mass and majority are prolate redshift 2 and above. And even much higher mass, you still get a significant fraction of prolate galaxies, although then you get many more spheroidal and oblate. So this was a very detailed study of the Candel's data set, led by a brilliant student, Haowen Zhang, who's now a graduate student at Arizona with Peter Baruzzi. How do we find this out? Well, basically, if galaxies are spheroidal, no matter how you happen to catch them, what orientation they have, they're going to always look more or less circular. Disk galaxies must have a roughly even distribution of axis ratios. You'll see some face on, some edge on, and everything in between. If you don't see large axis ratios short of a long axis, then they must be prolate. And that was our conclusion. The only way you get more or less round ones is if you see the prolate galaxy end on. And that's basically what we saw. I don't have time to go into the details of how this works. Every dot here is a galaxy observed by Candels. And this is the so-called banana shape that we expected, that tells us that these early low mass galaxies are prolate. This is a diagram where mass increases to the right, redshift increases downward, and galaxies evolve in this diagonal direction. Mass increases and time gets lower. What we see is that the more massive galaxies at late times do fill the whole region from circular to edge on. And the fact that the edge on ones look very attenuated, that's this red here, the color code is AV, really confirms that that's what we're seeing. Whereas here we see no indication at all of attenuation. And so this is from our paper where we explain how the dark matter simulate, the zoom in simulations are showing us this. So this is the stars on the right and the dark matter on the left. And what we see is that the stars are really forming this pickle-shaped galaxy. And if I had time, I would actually show you the evolution. But it takes a few minutes and I don't actually have that time right now. So let me skip the details, but what you're seeing here is that this prolate galaxy is forming inside a prolate dark matter halo. And this was our paper, Severinomi and Deckel, 2015, where we showed that when the galaxies are dark matter dominated in the center, most of them are prolate. But as soon as the center becomes dominated by baryons, they're no longer prolate. And we understand in some detail, especially in this Tomasetti paper, 2016, that that's how it works. Viraj Pandya worked with me in a paper that we published a couple of years ago. Viraj was, of course, a visitor at the CCA for the last couple of years. And he's going to be a postdoc at Columbia. But what we did is we looked for this alignment of prolate galaxies tracing the cosmic web. And we didn't see it, but we concluded that that's probably because there just weren't enough spectroscopic redshifts. Another 1,500 redshifts, a study by one of my students just showed, would be enough to really test this. So what I want to go on to show you is that we actually verified that there is this sequence of shapes when we look at the Condell's data. And we did this by training deep learning code, convolutional neural net, to recognize the shapes of galaxies in 3 different stages. The middle stage is what we call the blue nugget stage. And that corresponds to when there's a rapid infall of gas into the center of the galaxy, fueling a central starburst. So we call that the compaction stage, or the blue nugget stage. The previous stage, galaxies are mostly prolate. After that, galaxies are mostly disks. And this is a picture of what these simulations look like if we could see these galaxies close up, about 10 megaparsecs away. These are galaxies at redshift 2 from our simulations. This is what Hubble would see, these same galaxies at redshift 2. And this is what Hubble actually saw. So this is an example of a Hubble prolate galaxy, a Hubble central starburst, and a Hubble view of a disk galaxy at redshifts of about 2. So our code could identify that these galaxies were compaction phase, that's the green, pre-compaction is the blue, and post-compaction is the red. And this is as a function of stellar mass. And the prediction was in good agreement with the observations. There's some indication that there's a shift in the mass a little bit higher. If you look at higher redshift, this is 1.4 to 2.2, but basically we're seeing the same pattern. So it looks like the observations, and this is the entire Condell's data set, agree pretty well with the expectations from our simulations. We'll be able to do much better with James Webb Space Telescope. This is JWST NIRCam H-band compared to Hubble H-band. And this is a complex case where there's 2 compaction events, the yellow and the blue band, where a bunch of gas flows into the center, and there's a big jump in the stellar mass, that's in red. And you see it's complicated and difficult. So I say deep learning struggles with the mock HST images. But JWST, James Webb Space Telescope, it's just been announced that it's going to go up this December, mid-December. And it looks like it's on track. Anyway, as you see, we really nicely can determine pre-compaction, compaction rather, that's the green, post-compaction, that's the red. And then again, we see compaction, that's the green, and then post-compaction. So deep learning should be able to really do a great job when we start to have a significant number of James Webb images. Now, I want to switch to talking about another feature of galaxy morphology at high redshift, and that's these clumps, these bright regions. And a paper led by Yiqing Guo, summarizing the Candel's data in 2015, found that more than 60% of galaxies in this lower mass range, 10 to the 9 to 10 to the 9.8 solar masses, are clumpy down to redshift of a half. The galaxies, little higher masses, start to have a lower fraction that's clumpy. And sorry for that background noise. And the higher mass galaxies, a smaller fraction are clumpy, but still a clear majority of all galaxies, which are mostly these lower mass galaxies, are clumpy, at least down to redshift 1. So this clump phenomenon is really ubiquitous. And it's therefore a challenge for simulations to see if we can understand them. Now, it's not easy, even with HST data, to measure the clump properties. The problem is that HST's best resolution at these redshifts is about 1 kiloparsec, and clumps are mostly smaller than that. So we're getting a mixture of clump light and background light from stars that are not part of the clump. What we did is we trained a deep learning code on realistic mock images from our simulations. But we knew from the underlying simulation just how massive the clumps really were. And we were using multi-wavelength photometry. And we were able to do a pretty good job of disentangling the clumps from the background light. And so as you see, the true mass on the horizontal axis, the observed mass without the correction, is often high by a factor of 3 or as much as 10 or more. But with the deep learning code, we could almost always correct that and get the true mass. And among the many figures in our paper on this, published last year, is this one, showing that the clumps more massive than 10 to the 7 solar masses only make up a few percent up to 20% of the total stellar mass of these galaxies, and a smaller fraction for the more massive galaxies. I don't have time to go into this in any detail, but in our most recent paper, led by Omri Ginsberg, one of Avishai Deckel's graduate students, what we do is we compared the simulated, that's in dashed, with the observed galaxies. And here we're looking at the clump mass functions. We separate the long-lived clumps from the short-lived clumps. I don't have time to explain in detail, but I'll be glad to answer questions about that. And here on the right, we're looking at the host galaxy masses. And what you're supposed to see very quickly is that the basic picture of the clump masses and the host galaxy masses separately for the short-lived and the long-lived clumps agree really quite well between the simulations and the observations. Now I have to tell you the bad news. The simulations that I'm talking about are what we call the generation 3 simulations. Daniel Severino has run the same simulations, the same initial conditions, with different feedback prescriptions 5 times now. This is what we call generation 3, which was actually the second time we ran the same initial conditions. Generation 1 was a different set of initial conditions. And you see they're all somewhat above the stellar mass halo mass relation. There are these red points. The latest generation 6 simulations are in much better agreement with the stellar mass halo mass relation. And how do they do on the clumps? And the answer is horribly. So in black are the new generation 6 simulations. The solid ones are the long-lived clumps. The dashed ones are the short-lived clumps. And what you're seeing is that although the red ones were in excellent agreement with the observations, the black ones, and we're talking especially about 7 solar masses and above, are an order of magnitude lower or worse and in terrible agreement. And this is also a problem with the fire simulations. They had the same problem. They are not producing these massive long-lived clumps. So I propose that we try to cut back on the preventive feedback, the ejective feedback, and increase the preventive feedback. We're just in the process of starting to implement a whole new series of simulations where we appeal to various kinds of preventive feedback to try to get good agreement with the stellar mass halo mass relation, but preserve the clumps. I think this is an interesting challenge to theory. Well, that's the end of that part of the talk. I've got about 15 minutes to go on an hour talk. So I have time for a few questions if people have any right now. Otherwise, we can go on to planet habitability, and you can ask me any questions you like at the end.
Well, I just wondered if you could say a few more details in terms of your last point there about the feedback, because I mean, in principle, this isn't something that we should, nature isn't tuning up or down, right? So what do you mean exactly with less effective or more effective in this sort of balance between ejective and preventive?
So as an example of the preventive feedback that I have in mind, Sebastiano Cantalupo pointed out a decade ago that we're not really taking into account the effect on species like oxygen 5 of the radiation that's coming out of the galaxy that will tend to ionize that to oxygen 6 or 7. Oxygen 5 is the most important coolant. Once you get above temperatures where Lyman alpha cooling from hydrogen and helium is effective. So once you get up to several times 10 to the 4 Kelvin, up to the 10 to the 5 Kelvin range, you expect that it's mostly going to be oxygen 5 that's your main coolant. Of course, about half the metals is oxygen by mass. And to do this properly, you want to do local radiative transfer. But Nick Gnedin showed a little after that, 2012, that you could modify the cooling tables, roughly taking into account what you expect to happen. And there have only been a couple of attempts to run simulations with this kind of preventive feedback. So what I'm talking about preventing is cooling of gas to become available for star formation. That's the other way, not involving ejective feedback, that you can prevent too many stars from forming too early. And so that's what we expect to implement using this scheme that Gnedin developed, which has only been used, as far as I can tell, by 2 groups in the literature and only for a couple of simulations. And they got opposite results. So I think it's still quite an open question how this kind of preventive feedback would work. And that's only one example, but just to answer your question, Chris, that's the kind of thing I have in mind. Preventing stars from forming by processes that don't involve feedback from the star formation itself.
Thank you.
Other questions? Incidentally, a proposal that I submitted together with my colleagues, of course, including Avishai, is an ATP proposal. So if any of you are on the team, the astrophysics theory program, please smile on our proposal. Okay, well, not hearing any further questions now, of course, you'll have plenty of time to ask at the end. Let's go on to planet habitability. So most of the extrasolar planets we know about were discovered by Kepler, almost 4,000 planetary systems. Kepler looked at this fairly small region in our galaxy, about 100,000 stars, and they looked for planets to cross in front of the star. Now, we used to think that most planetary systems look like ours, with rocky planets on the inside in beautiful circular orbits, widely spaced, and gas giants on the outside. And we've never seen another system like that. Most are much smaller. The most common type of planet seems to be 2 to 6 times Earth's mass, as super Earth. No such planet exists in our solar system. Some planets are in the habitable zone around their stars, in which water would be in liquid form, but most of these planets are probably not hospitable to advanced forms of life. For one thing, they might not have optimal abundance of the long-lived radioactive elements, thorium and uranium, to power plate tectonics and permit a magnetic dynamo. Too much thorium and uranium would result in a lava world with frequent flood volcanism, which caused the greatest mass extinction events on Earth. Our living Earth may be a rare Goldilocks planet with just the right amount of thorium and uranium. I'm going to come back to that in just a second. But let me point out that there's also been a lot of papers about galactic habitable zones, not too close to the galaxy center, where there are too frequent supernovae and active galactic nuclear outbursts, nor too far from the center, where metals may be too rare to form rocky planets. I note, though, that Raymond Simons just led a paper that that's on the archive. I don't know if it's accepted yet, that shows that most measurements at redshifts greater than 0.6 find that the metallicity does not fall with radius. It's either flat with radius, or it even grows with radius, with the center having a lower metallicity than the outside. This is looking at the gas phase metallicity. This is also a challenge for simulations. All the simulations I know, we're just checking our own simulations, but the TNG simulations, like many earlier ones, show at all redshifts mostly a radially falling metallicity. Metallicity here always means O over H plus 12, log count of O over H plus 12. Okay, well, this is what our simulations show when we change the amount of heating by uranium and thorium, the long-lived radioisotopes. So roughly half the heat of Earth is coming from uranium and thorium radioactivity in the mantle. And that keeps the mantle not too hot, so that there's a thermal transfer from the very hot solid core to the hot outer core, where there are these convective outflows of heat into the mantle, which is cooler. And then that heat coming into the mantle is causing these convective cells that transfer heat into the crust and lead to plate tectonics. And if you increase the amount of radioactive heating in the mantle, you then suppress the outflow of heat from the core, because the mantle becomes as hot as the core, the outer part of the core. And that suppresses the geodynamo. It also leads to flood volcanism. You get very extensive volcanism. If you cut back on the heating from uranium and thorium, then you get basically what is known in the trade as a stagnant lid planet, and you don't get anything like plate tectonics. That's been very important in the history of Earth for recycling carbon. This is, that was of course an artist's conception. This is a figure from our paper. So I pointed this out at one of the first meetings of the research group at Santa Cruz that's just been started on astrobiology, led by Natalie Battaglia. Natalie led the Kepler program. She got her PhD in Santa Cruz 20 years ago, and she joined our faculty a couple of years ago. And she just got our first big grant from NASA, a $5 million grant. Anyway, our paper is the first paper to come out of the meetings that she started on astrobiology, where I pointed out that given that these radioactive elements form in rare processes of only a few per million years, neutron star mergers, you would expect incomplete mixing and a fairly large spread, which indeed we detect when you look at the spectra of stars in the amount of these our process elements. And so the middle line is Earth's thorium and uranium. And what you see is that if you go up just a little bit, even just a factor of 2, you get no geodynamo for hundreds of millions of years. And if you go up much more than that, you basically kill the geodynamo for a billion years or more, for the reasons I explained. And if you go down, then you also probably kill plate tectonics, although we don't understand plate tectonics that well. Now, I do want to point out that there's a recent paper from Borexino, a neutrino detector originally designed to detect the high energy neutrinos from the sun, but they can also detect the highest energy neutrinos coming up from the Earth. And those highest energy neutrinos are only produced by thorium and uranium radioactive decay chain. And they think that the amount of thorium and uranium is actually almost twice what we assumed, which was based on the carbonaceous chondrites. So that's potentially a problem. I'll go into more detail on that in response to questions. Anyway, europium, as you see, going back to the slide I showed earlier, is almost all our process. In other words, probably from merging neutron stars. That's this orange part. And that's the easiest of these our process elements to detect in stellar spectra. So we suggest that you should measure the amount of europium, and if it corresponds to what we think is in our solar system, both from the composition of the sun and also from the chondrites, then you have an optimal amount of uranium and thorium for an Earth-like planet. Although a super Earth would have about twice as much heating and probably not be very suitable for life. Anyway, so we proposed to measure the europium better, and our paper was based on a 1D study, and we also proposed to do 2D and 3D studies of a wider variety of planets. Well, that's the talk, and let me just conclude with a couple of concluding thoughts. Without dark matter, we wouldn't exist. With only the ordinary matter, the universe would be a low-density, featureless soup. Dark matter started to form structures very early. Galaxies form within the halos of dark matter. Stars form within galaxies. Stars made elements beyond hydrogen and helium, carbon, oxygen, and so on. Rocky planets formed from these heavier elements, and life began and evolved on one such planet, namely ours. So dark matter is our ancestor and our friend. And then the second thought, science is much stranger than fiction. But before the discovery that most of the density of the universe is invisible, no one imagined this. What else remains to be discovered? Well, with that, I am delighted to take questions. So,
thank you very much. Thank you very much, Joel, for the very interesting talk. Do we have any questions from the, so I see Rachel has her hand up.
Hi, Rachel.
Hi, Joel. I know you can only see my back, if that, but thanks for a fascinating, incredibly rich talk. I wanted to ask a question about your last topic. So suppose we were to plan a telescope that could search for signatures of life on planets, which might happen. We will find out soon. What are the implications for what people sometimes call Eta life? So the fraction of planets in the habitable zone that might harbor life based on your work. And is the idea that you could search for stars based on their europium content and then point your telescope at particularly at those stars to search for life? Is that the idea of your study?
Yes, and we say that explicitly in the paper. Incidentally, the paper is published. First author is Francis Nimmo, N-I-M-M-O. I'm the second author. It's in AppJ. the most typical rocky planet is a super Earth. And we don't really know what the distribution of uranium and thorium is. Assuming there's one good paper, we cite all these papers in the paper, that shows that it does look like europium is a very good tracer. If that's the case, Earth is on the low end. So if you, and the simple scaling for the super Earths would be the amount of the radioactive heating is going to go for the same composition with the volume. In other words, is R cubed. The heat loss goes as the surface area, R squared. And so the net is a factor of R. If Earth is indeed at the low end, then that would be very favorable for life to be suitable on a super Earth, at least from the point of view of radioactive heating. But we really need to pin this down better. The measurements of the europium are mostly at relatively low resolution. But it turns out that we have extremely high resolution spectra, better than R of 100,000, for many of these Kepler planets, planetary systems, the star. And we started to look at those spectra, and with those you can actually do much better europium measurements. So that's one of the things we proposed to do in the proposal that we submitted. Francis Nimmo was the PI for the XRP program. So that'll help to clarify this. And then also, the other thing that we need to do is to actually consider the internal structure of planets of that type, which is not likely to be exactly the same as that of Earth. So 2D and 3D analyses will need to be done, and we're capable of doing that. Anyway, that's what we would need to do to answer the question that you raised. Well, I can go on at some length on that, but let's see if there are other questions. If not, I'll be glad to come back and tell you more. Let me just add one more thing that's kind of interesting. Suppose there's two separate issues concerning life. One is formation of life. A quite separate issue is development of life over billions of years to complexity. It may very well be that life had a good chance to start on Mars, and probably did start. Mars' surface is not now habitable. It is not suitable for life. There's too much UV, there's not enough atmosphere, it's very cold. But subsurface Mars might be great for life if it got started during Mars' earlier habitability era. How would that life survive? What would be its main source of energy? And the answer is radioactive decay. And also, it's very likely that the majority of life under Earth, under the surface of the Earth, life is seen down at least a kilometer or two, in some abundance, actually. And it seems that it's mostly powered by radioactivity, radiolysis, splitting water and other molecules, and that then providing energy source to recombine for bacteria. And that's what we actually see. The radioactivity turns out to be relevant for preservation of life, even in situations where the surface of the planet may be quite hostile. I went on at greater length than I expected to, though. So if there's more questions, this will be a good time to talk about them. I hope that people were as shocked as I was at Colin Hill's presentation yesterday and this new paper.
I did have a question about that part, but I wanted to see if anyone else in the classroom had any questions before I asked.
Well, not hearing any, let's go ahead.
Okay, so I wondered, the plot that you showed of I think it was the energy density in different forms versus redshift, and at the redshift where the early dark energy kind of had a significant contribution. There was sort of it wasn't a simple shape. It wasn't just like a simple rise. It kind of had a complicated little wiggle there. I wondered if there's a
I'm
way
sharing
to,
my screen again. So
yeah,
you- and it's
yeah,
the spot
exactly.
on the right. Yeah.
Yeah, so the fact that there's these kind of three peaks at different redshifts, I mean, is there a simple way to understand why it shows this kind of more complicated evolution than, say, radiation and matter do? I just was surprised, but I know almost zero about this.
So the answer is no, it's not the sort of thing that you do if you didn't want to try to understand this Hubble tension. But it's really easy to make it work. So the basic trick is that you have some kind of potential, and it turns out that a 5 to the 4th potential probably works. What was actually used in the paper that we used, which is the Poulin et al. Or the Smith et al. Paper, or the Bergia et al., that's all the same group. What they used was an axion type potential. But it turns out that you can, and actually Colin Hill's seminar in Aspen yesterday explained this very nicely. So he's a colleague of yours, and he'll be glad to explain it in detail. And he showed that you could just as well use a 5 to the 4th type potential. But in any case, the idea is that the scalar field gets, you just adjust it to not be at the bottom. And we can go into reasons why you would expect it not necessarily be at the bottom, but that's an early universe issue. The point is that if the scalar field is light, it can get trapped at whatever value you set it at by this thing called Hubble friction. And that's just standard. If you you look at the standard literature on inflationary cosmology, this is always something that is part of the story. So the scalar field, you just adjust it to sit above the minimum of the potential. And you adjust the energy density to be whatever you want it to be. And you can adjust it to be just such that it makes a negligible contribution to the energy density of the universe until the radiation starts to decrease and the matter density starts to increase. And it turns out that's the optimal place from the point of view of solving the Hubble tension to make this happen. So it's really easy to engineer because you have this natural phenomenon that the scalar field is going to be stuck. And then as soon as it begins to be important and is making an important contribution to the energy, it will start to roll down the potential and quickly disappear. And that's just the behavior you want to make the Hubble parameter be a little bit larger than it is in standard lambda CDM. So does that help to explain how this works? It's easy to engineer. And in fact, this team that we work with had already done all this engineering, and our contribution was to run the n-body simulations to see what the implications are for nearby universe observations. Nearby, I mean low redshift out to redshifts of 6 or 7 or so. That was our contribution.
Thank you very much.
Sure. So this is the slide that summarizes. And what you're supposed to see is that early dark energy, that's the black curves, has higher power. The red and the black and the different black curves are because we're running simulations of different length scales to get these different size boxes, to get these different mass scales.
Could I just have you explain what N in the top panel actually is indicating? Is that
it's the number density of halos as a function of mass.
Halos.
And it's the number
so
density.
The observable is galaxies or clusters.
So the z equals 1 curve, I don't know if you can see my pointer.
I can.
So that's cluster mass. That's a mass roughly of the Virgo cluster, but at redshift 1. So that's a mass that would be a cluster that's more massive than Virgo.
That we get from cluster counting.
That's right. So this is saying that there'd be 50% more clusters of that mass at redshift 1. And the eROSITA satellite is supposed to be able to get essentially all the clusters, that mass and above, out to Redshift 1. It's going to have 100,000. It's been up there for almost 3 years now. And one of these days, they're going to start publishing, I assume. And the challenge, of course, is going to be to calibrate their X-ray measurements so that we can convert them into mass measurements. That's always the challenge. And the hope is that by some combination of gravitational lensing, Sunyaev-Zeldovich, and so on, for some subset of those clusters, we'll be able to convert the X-ray data to measurement of the mass. And there should be huge numbers once we start to get this new all-sky census. Incidentally, eROSITA is also measuring over 1 million AGN. It'll be an all-sky census of AGN.
So we're well over time. If people shouldn't feel shy about dropping off if you need to go, but Paco, you have your hand raised, so go ahead, please. And
yes.
Those who want to stay, feel free to stay. That's the freedom of Zoom.
Yes. And
sorry, regarding this particular slide, so does this result not depend on the particular value of sigma 8, maybe of omega matter that you are? I guess in the two simulations you have fixed some parameters.
So the story is that what we do is we fit the early dark energy scheme to the Planck data. And what we should do now is redo the whole story with the ACT data, especially if ACT indeed is capable of publishing in the next few months their data release 6 with 4 times as much data. And if that data is consistent with what they published so far, it will be a more than 20 sigma detection of early dark energy. And it will certainly mean that we and probably lots of other groups are going to want to do these kinds of simulations. I mean, my own intuition was that this was definitely worth exploring. And I was delighted that I was able to convince my colleagues who are capable of running these big simulations, in particular Anatoly Klipin, to actually put a lot of effort into running the simulations. And this paper from Colin Hill et al. Should be very helpful in convincing the Japanese to let us have time on their new supercomputer, which is currently the world's fastest supercomputer. So that may allow us to actually run the appropriate simulations.